Hi, this is Aaron from Franklin Maths, and this video is on finding the critical region using the binomial distribution. Okay, so based on the previous videos, you should have a decent understanding of the binomial distribution and be able to perform a hypothesis test. But one thing I haven't mentioned is, what does the binomial distribution look like? So I'm going to explore that now. So here is my distribution. X is approximated by the binomial distribution. Remember, this is n here. So this is the number of trials. And P here being the probability of success, whatever that may be. So this could be a coin, for instance. Now, if I flipped a coin 100 times, you'd expect to get 50 heads, 50 tails. That's what you'd expect. Obviously, that might not happen. Okay. Now, have a look at this picture. Now, this is the picture that you get if you used to plot all these different values here. So this one here, this tallest bar here, is the probability that X is equal to 50. And if you have a look, it's still a very, very, very small percentage. And you'll notice there's quite a steep drop off. Okay. Now this diagram isn't quite correct because these bars should have gaps between them because this is a discrete distribution. You can't have 4.5 heads, so this is a discrete distribution. So this should have gaps in between, but the website I've taken it from obviously didn't have gaps. I'm just showing you it here. So when you guys have been working out the probability of X is greater than or equal to, say, 60, you've been finding all of these probabilities added up. Okay, so that's what your calculator's been doing. So that's what it looks like. Now this one here, this particular distribution is quite nice. It's nice and symmetrical. It does sort of curve off quite nicely. We'll certainly look at this in the second year videos. However, I want to show you some other ones. So I'm just going to pause the video a second and just show you some other ones. Okay, so this is the binomial distribution image generator on GeoGebra. The author is Michael Borcherdts. Thank you for this. So all I'm going to show you is I can move the probability around. As you can see, by moving the probability, it does begin to change the shape. It doesn't seem like it at first, but it does. And you can see it becomes more uneven. And you certainly over here, look, you get an entirely different spike. It no longer is symmetrical. If I move n around as well, so one trial. And if you look there, if I was to do 17 trials, my probability of success was 0.97. You can see that there. So I can just play about with this distribution a bit. And there you go. Now, I would spend quite a long time in lesson looking at bits and pieces. But if I just take, let's take n as 30, and let me take p as 0.6. Whereabouts is the highest bar in terms of probability? It's this one here. And that comes out as 18. Well, where does the 18 come from? Well, it comes from multiplying n and p. If you've got a number of trials, you've got probability of success. If you multiply those two together, it would give you effectively what you'd expect. We call it expectation. So it gives us basically the mean, the expected number from there. So if you want to find this on GeoGebra, just email me and I'll send you the link. It's easy enough to use. All I'm really trying to show you is what a binomial looks like. I'll be drawing lines on mine. Okay, I'm just going to flick back to the PowerPoint. So hopefully now you've got a reasonable understanding of what a binomial looks like. I tend to sketch them a fair bit when I'm using critical regions. So moving forwards. Now you've seen questions like this before. We think the coin is biased towards heads. We're going to throw it 100 times. How many heads would be needed for us to obtain? Would we need to obtain for us to suggest there is enough evidence that the coin is biased at the 10% significance level? Not my greatest bit of English there, but you get the gist of what's going on. So this case here, we're not given a number of trials. We're actually trying to find what would the number be. Okay, so we can set up a hypothesis test in this case. I'm going to rush this ever so slightly. We're going to have H0 is where, sorry, missing my colons out, is where the probability is still 0.5, and H1 should have really defined that X is number of heads. Make sure you watch the previous video before doing this one, otherwise this will make no sense. So we're looking where the probability has gone greater than 0.5. Okay, we're trying to find really, well, how many do we need before we say, hang on, yeah, this is biased? We looked at the beginning of the last video, and we suggested some possible ideas. Okay, now lots of students always ask me, well, where do you start? Where do you choose your numbers? Well, I know that the expectation or the mean of a binomial is you multiply. So this is a binomial, x tilde b, np 100, 0.5. Now, if you multiply these two together, it'll give me 50, and that's called the expected value, or sometimes called the mean of a binomial. I'm going to call the expectation of x. Okay, it gives us an idea where we need to start, because you won't always have a nice distribution like this. So I'm just going to try a few numbers in my calculator. First thing I'm going to do is try, and I have no idea whether this is right or wrong. I'm literally just guessing and just see where we go. I'm going to go try, now looking over here, this obviously drops quite low, so I'm going to try 60. X is greater than or equal to 60 in my calculator, and just see what number I get, and see how close I am to the 0.1. Okay, just going to grab the calculator. Oh, and it's gone again. That's back, there we go. So over to stats mode, distribution, binomial, so BCD. My lower is going to be 60. My upper, well, the maximum number of heads I could have got was 100. Number of trials is 100. And the probability is 0.5. Just work that through, and that comes out as 0.028. So 0.028. So that's a 2.8% chance of that happening. Which is good, because it is in the where we would reject H0, but it's not the number we would use. So let's just try. Let's bring this down to. Let's try 55. Just exit. So this time I've gone a little bit above. Look, 0.18. So 18%. So we've got an 18% chance of getting 55 or more, but only a 2.8% chance of getting 60 or more. So the value is somewhere in between those two. So I'm going to go for, looking at the weightings of these, I'm going to go for, in fact, it makes sense just to go for 57. Trial and improvement, they used to call this. So this time 57, and I've got 0.966. 0.0966, which is a 9.66% chance. Okay, so it looks like it's 57. However, we must check 56. It would be silly not to. I know you can see well there, and yeah, there's, that one's obviously going to be closest. It doesn't matter. It's worth checking. Let's just try 56. And this time we've got I'm just going to write down the percentage, 13.6%. So in this case here, we would need to get, for us to reject H0, we would need to get 57 heads, which doesn't seem that many really, but there you go. Okay. Now that value there is called the critical value. It's the value where we change from going accepting H0 to rejecting H0. Okay, and we would call this, if I just split this into two, all this section over here, we will call this the rejection region. Basically where we're going to reject H0. And over this side, we would call this the acceptance region. Okay, this is quite nice to do. I think it's a little bit easier than what we did in the previous video. I say if you manage to nail that previous exercise, this should be fairly nice to do. It is a bit of a guessing game, but I always get my students to start by looking at the expectation. It gives you a nice point of where you can see where the sort of peak of this graph is. Okay, moving forward. So here we go. So we've got a snooker player. He's got a 24% win rate. Going to try our new cue, play 50 games, and then we're going to do the same thing here. Okay, we'll look for an improvement. So X is going to be equal to the number of games won. So I'm just trying to show you how I would do this now in exam situation. X equals number of games won. I should really write snooker games, but I'm rushing. H0 is that this particular snooker player still has a winning percentage of 24%, so 0.24. So the new cue, has it made them a better player? So this is where the probability is now greater than 0.24. Okay, let's write down our binomial. So it's going to be NP, so we're going to have 50 trials and 0.24. So we're going to try and find basically the critical value in the critical region, acceptance region. Okay, and this is where students say to me, Aaron, I don't know where to start. What numbers am I guessing? And in this case here, let's just find out the expectation, the expected value of X. So let's just multiply these two out, which is going to give me 12. We'd expect them to win. If they've got a win rate of 24%, we'd expect them to win 12 games if there was no difference. So I'm just going to try and sketch this as best I can. So I'm going to use lines rather than bars. Now, I'm not quite sure what it's going to look like. I'm just doing this just to show you what I would do in an exam. So I would have 12 here. I would have sort of 0 here and 50 over here. We know that the highest line is going to be at the 12, and it's going to be something like this. I'm not saying my picture's perfect or even remotely looks like what it's going to in the exam, but you can see I've used lines and I've got gaps because I've got discrete distribution, but I've got a peak here, so I can begin to look at this. If you want to be more accurate than mine, then feel free to. I'm just trying to show you what I would look like, what it would look like. Okay, so we're going to try some numbers then. So we're looking for one where it's gone higher than 0.24. So we need to go sort of above 12. We want to be going over here somewhere. So let's try, I don't know, we need to go higher than 12. So let's try the probability that X is greater than or equal to, let's go for 15. And we're just trying to make that at the 5% significance level. So let's just grab a calculator. Just go backwards from there. So my lower value in this case is going to be 15. upper value is 50. We've got 50 trials, and that's 0.24. And that gives me a, well, it's around 20%, so 0.201. 20.1%. So that's quite good, because it's sometimes if you go too far here, the numbers are tiny and you're not sure how far to bring it back. This 20% isn't that far off. And once you've done a few of these questions, you'll go, oh yeah, I'm getting closer and closer. Okay, so let's go for it makes sense. I'm going to go for 17, I think, and just see where we end up, which is quite nice on these particular calculators, because what we can do then, we can just keep pressing back. There it is. Okay, so I can just change that to 17, and there we go. We've got roughly 7.2% chance. So I'm just going to write this down. So 7.2% chance. So now I'm into the, well, I'm not quite in the, sorry, I'm not quite into the critical region yet. I'm nearly there. I'm very close to it. So let's try 18. Exit. And there we go. So we've got this time a 3.84%. 3.84%. Sorry if there's a bit of a small technical glitch there. I've had a little bit of an issue there with recording software. I didn't want to record my microphone. So here, in this case here, where it changes from being able to accept H0 to rejecting H0, 18 would be the critical value. So x equals 18 is the critical value. So you might be asked then to state the critical region. So in that case, x is greater than or equal to 18. It's the critical region. And then the x is less than 18. Just change my symbol there. Let's just rub that out. It looks scruffy. X is less than 18. That's my acceptance region. Okay, so it's very similar to what we've been doing before. Okay, so with this question here, slight change here. I've got a dart player, and I've been trying a new set of darts. I'm just going to change that slightly. I'm just going to change that to a 10% level. I meant to change it a second ago. So in this case here, we've got X being the number of bullseyes. We've got H0 then, is that the probability of winning hasn't changed. So that's 1 in 5, which is 0.2. And in this question here, we're going to see when there's been a change in win rate. So it's not equal to 0.2. It is a 10% significance level. It was 1%, but it's just easier to work with the 10% on this particular style of question. So this question says, can you find the critical regions in this case? Because we're going to have two cases here. So we've got a binomial distribution, x tilde b. It's NP, so that's 50 trials at 0.2. So first of all, let's find out the expectation. The expected value. So multiply these two together, which gives me 10. And I'm going to attempt to draw a binomial. just draw up here a little bit. So there we go. So it's going to, if this is 50 over here, this is 0. So 10 is approximately here. So that's where my tallest line would be. And then I have these others sort of like this. It's not perfect. Just so you can see what's going on. Remember, each one of those lines tells you the probability of each one happening. And there's a very, 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 very slim chance of us getting 50, of the dart player hitting 50 bullseyes. So in this case here, we're going to have two critical regions. We're going to have a sort of lower cutoff point here and an upper cutoff point here to see whether there's a change or not. So remember, we're going to take the 10% level and split it up into the 5% and the 5% either way. So first of all, I'm going to look at what we call the lower critical value. And as before, it is literally just a guessing game. Just going to draw a line down there and work on either one. Okay. So what I'm going to try, and remember, I need to go below 5% here. I do need to split it. So I'm going to try 5. I'm going to just chuck the percentages straight away. So grab the calculator. So exit. Let's have a look. So we've got a lower value. So my lowest value is going to be 0. The upper in this case is going to be 5. Number of trials is still 50. And my p-value is 0.2. And we've got 4.8%. That's pretty good. So that would be then in the rejection region. So I just need to check that 6 isn't in there as well. I suspect it's not. But sometimes you get on with these, you get a number which is, say, with maybe 7%, and then the next one, you think, oh well, that's probably not going to be in it, but it ends up as like 5.5%. So let's just try 6 this time, and that comes out at 10.3%. Okay, so in this case here, x is less than or equal to 5. So that's your rejection region. And this one here, this is the critical value. And that's the lower one. Okay, so easy enough to do. Let's just do the upper one then. Don't assume that this is going to be symmetrical and we can just go for 15. I mean, I will try 15, that's probably where I start, but don't assume that all the time that they are going to be symmetrical. So let's go x is greater than or equal to 15. So x is there, lower is going to be 15, upper is going to be 50, and that gives me a 6.07%. 6.07% chance. So that would be in the acceptance region. Now we need to dip this below 5%. So we need to go up in values here. If you look over here, these bars are getting smaller as we move away from the mean. So let's try 16. Which is 3.08%. 3.08%. So in this case here, x is greater than 16 is the rejection region, and x equals 16 is the critical value. and that's the upper. Now you might be asked then to write down what's the acceptance region. In that case, we can just use, it needs to be between 15 and 6. So if they get anything between, if they get 6 darts, no, there's not been a change. 15 darts, no, there's not been a change if that's anything there. And it does seem quite narrow actually. But if you think about the probability is 0.2. Okay, so hopefully it makes sense. It's quite nice to do. It's not particularly challenging, I find. A couple of things I want to mention. I want to go back to this one here, this snooker player here. Okay. Now, what's interesting in this question here is that the idea of this new cue, that this new cue is some sort of magical instrument that's made the snooker player a better player. Okay, it might not have been the fact it was the cue. And in fact, we actually have no proof it was the cue. Okay, it could have been down to anything. It could be down to the fact that the snooker player is on a better diet. They might be a bit more focused. They might be wearing glasses. They could have gained in confidence. We don't know. Okay, so all this about sufficient evidence. We just need to be careful. And also here, there's another problem. They play 50 games. But these 50 games, we don't know really anything about these 50 games. With the opponents could have been poor. There could have been all sorts of bits and pieces. So there is actually a chance that we have actually come to the wrong conclusion on some of these. So even if the win rate is still 24%, this sample could suggest that we have an improvement, when actually it's not true. So we just, remember, we've got to take this with a pinch of salt here. It's all about the sample, really. Now, this would happen if the number of wins is in the critical region. So if the number of wins is in the critical region, we've actually rejected the null hypothesis, even though it's correct. Now, this sounds really complicated. So I'm going to refer to my key point here. So the probability of rejecting a correct null hypothesis. So the null hypothesis is correct, but we rejected it. And that's probably possibly down to sampling, something like that. Now that is going to be the same as the probability of the test statistic being the critical region. It is always small or equal to the significance level of the test. Now this sounds really, really complicated. But I promise you it's not. And I'll show you, let me just go back to my 2 previous examples. So if I go back to here, the probability of me incorrectly rejecting the null hypothesis is going to be 3.84%. And this one here, in this case here, I'm going to add these 2 percentages together. So for me to, and I'll just write this on here, so you might add this to your notes and definitely highlight this, because this is the fiddly part of the course. So the probability, probability of us rejecting a correct null hypothesis in this case is just going to be adding these 2 percentages together, so the 2 critical value percentages together. So it's going to be 4.8% plus 3.08%. So which is 7.88%. So that's the probability that we've rejected a correct null hypothesis. Now, as I said on that key point slide, it should be either lower or equal to the significance of the test. Well, the significance level is 10%, and here it's 7.88, so that's good. And if I go back to the snooker game again, so this 3.84, this is us. That's a probability of us rejecting a correct null hypothesis. It is lower than the significance level, so it's not that difficult to do. It's just the value from the critical value. Okay. So I've just got one last question for you. There are a lot of questions here, but it's not practice. Obviously, does make payment in this case. So I've chosen a soup factory. Every 12 in 200 tins is faulty. In this case, I've written faulty is dented. I just wonder how you get faulty soup. We suspect that the labeling machine is the problem. It's been serviced. Sample of tins, and what is the maximum number of dented tins needed for us to reject the null hypothesis. So if you want to pause the video and have a go at that one, you can do. We have done a couple like this before, but I'm just going to go back through it. So we're going to have x is equal to the number of faulty tins. H naught P is equal to 0.06. H1 we want in this case I think we want to improve the number of tins which aren't dented. Okay, so we're going to try and find the critical region in this case. So we're going to have x, b, n is going to be 50, p is going to be 0.06. So in this case here, just a quick sketch of the binomial. Remember, in this case, the expectation, we're going to multiply those two together, which is only going to be 3. So there's 0. There's 3. I really apologise for that line. And there's 50. And look, I can only get a couple of lines in here. There's 2. There's 1. And some more there. So it's going to drop off quite a lot there. Just put a few in there. Okay. So in this case here, we're going to shoot for a number which is less than 3 in this case. So let's just try 2, to be honest with you. One thing I'm doing here, I'm putting a significance level, which is quite interesting. I'm going to use a 1% level then. So what happens if you make your own questions and rush? 1% significance levels. Right, so let's work out then. Probability that x is less than or equal to 2. So we've got a lower value of 0, upper value of 2, 50 trials, and go away a second, and 0.06. So yeah, it's quite a high percentage, that one. So 41.6%. So we're going to have to go for 1. Ignore that line. Still not used to using this tablet yet. Wow, 19%. So if we've got one faulty tin, we're still not going to say it's fixed. So, yeah, this is a really poorly written question. I am going to be a bit naughty on this one, I think. And that comes out as about 4.5%. So in this case, there's no critical region. I'm just going to cheat here. I'm going to put a 0 on that there. So in this case here, the critical value is 0. So I need to find 0 tins for us to reject the null hypothesis. Remember as well, this number here, so we've got x equals 0 is the critical value. And also then, there is a 4.5% chance of us rejecting a correct null hypothesis. Which is quite nice if it comes up in the exam, because it's extra marks for doing the same maths. all this here, I mean, the calculator's done the bulk of it. All this here is all the stuff that we've already covered. You might get different marks for all these different bits. There comes my questions. There we go. Yeah, 5% level. Silly me. Never mind. Okay, and I've finished the rest of it off, so don't worry about that bit there. Okay. So yeah, I mean, it is quite nice to do. It's not overly difficult. Just watch out for two-tailed tests. That's best advice I can give you, really. The first question in the worksheet is quite nice. It's just get on with the maths without the context, and it will give you the idea of using the expectation. So the expected value of a binomial is just NP. It's worth starting there when you're trying to find critical regions, and a little sketch as well. Obviously make yours a bit neater than mine. Okay, so what I'd like to do is complete exercise 22C. Any questions, send me an email. Thank you very much.